Welcome to my new calculus channel. I'm John Gabriel. In this video we're going to be talking about my new limit theorem. Actually, it's not really that new. It's about 2 years old or so, but considering that's relatively new. This theorem actually debunks all the epsilonic arguments that are used in real analysis and also in Cauchy's derivative definition and Riemann's integral definition, which is actually the reason this particular limit theorem came to be. Now, the statement that you're looking at there in mainstream calculus doesn't have a two-way implication. It's only a one-way implication. In actual fact, it's wrong. It should be a two-way implication. And in terms of the derivative, this delta f of x is actually equal to that, which is the finite difference. And so the distance between the finite difference at a given point and the limit must be less than some epsilon. Now, if you remember from Cauchy's kludge, the Applet Cauchy's kludge, which is also on my YouTube channel, I explained to you that this is a very bad way of defining the derivative. Cauchy or Cauchy, however you pronounce it, it doesn't matter, really made things worse by introducing the limit definition. He really didn't improve anything. And the above definition, stated correctly, as it is there, says nothing more than the following in plain English words. As the distance between x and c decreases, so does the distance between f of x and L, with the result that the finite difference, which you see there is f of x minus f of c divided by x minus c, approaches the value of L. Ironically, the finite difference is used to determine L. So it's circular. It's actually a circular definition, and Cauchy did not notice that. So in order to use the definition ED, one must know the value of L beforehand. However, in order to find L, one must use the ill-formed definition, which is given there, in terms of the limit. And so it's very circular and hence flawed. And this little funny graphic here explains it. Note that in this definition here, epsilon is a function of delta and vice versa, and I will prove that to you in a document shortly. In fact, we can go about doing it right now. From ED, I derive an inequality that enables one to express epsilon as a function of delta and vice versa. So if you look at this inequality, oops, there you go, that, then I say from ED, it's true that we can square both sides of this to get that. Likewise, we can do the same with this inequality. And so we arrive at two inequalities here, inequality A and inequality B. We can add A and B, just simple algebra. And we arrive at this inequality. And finally, we arrive at this inequality here, which is the equation of an ellipse. A special kind of ellipse, in fact, a circle. And what happens here is that we take the square root of both sides, and we have epsilon as a function of delta, x, and c. So this really summarizes the new limit theorem, which I'm going to demonstrate to you and show you that it works for any function you like. It is actually a geometric definition of the limit. And I'll show you using an applet how it works. Alright, so why don't we do this? Why don't we leave that alone now and come to the applet directly. This graph here that you see in blue is the graph of the square root of x. Now, if we have a particular point and we move it away, what happens is that the area of this circle increases as we move away, and so does the the blue area or the shaded area, which defines the limiting region for epsilon delta. You will always find epsilon delta coordinates on the circle. So as we bring this point towards the red point, we'll see that we reach the limiting value. Yes? So it doesn't matter where C is. Let's move C a little bit away. Let's move it there to about almost a half. Okay, let's bring that to a half. Whoops. And we see the limit there is 1. So this region here should be 1. Well, if we introduce the grid on again, whoops, put the grid on and the axis, whoops, mistake. I'd have to label the axis, I suppose. Okay, so let's put the labels on the axis. Show the axis. Let's just do the y-axis. Show the numbers. So you see it's 1 there, right? So if you bring it to 5, the limit is 1. Okay. And similarly, if we move that away over there, put it over there. So the limit there would be approximately 2, yes? I'm sorry, 1.2. And as you bring it together, it's 1.2. This particular limit theorem works for any function. It doesn't have to be a special kind of function. It can be any function, okay? So let's type in another function over here. Let's type in f of x equals to x squared. Okay, so there. What happens there is as we move away, the area of the circle increases, right? As we move close again to that point, whoops, we get to the limit, yes? Let's see there. Okay, so we're almost at the limit. I'm trying to get it exact. There you go. So the limit there would be that value. Of course, we could move this along here. Let's get that out of the way for a second. Put it on 1. Yeah, and now get that out of the way and move it away. Watch the area increase, and now as soon as we get to 1, yeah, as soon as we get to that particular point, we're going to get the limit of 1, right? Which corresponds to 1 on the y-axis. Okay, so this particular theorem will work for any function. It doesn't matter what function you choose to pick. It will always give you a relation in terms of epsilon delta, and there's nothing else to do but watch it work analytically or geometrically, as you see me demonstrating to you right now. Yes, this is the distance. As the distance between the 2 points increases, see the pink distance here? So does the area of the circle. And as the area of the circle decreases, we know we are almost at the limit. So that when the conic or the circle becomes degenerate, in other words, just a point, we have the limit. And this is the statement of the limit theorem, which is what I showed you in this document over here, the one I derived using simple algebra. Okay, and so we have that new limit theorem, which replaces all the old limit theorems in calculus. It's not used in the new calculus because the new calculus doesn't use limits, but it's useful to know if you're still studying towards a math degree where you have to understand real analysis and why the limit arguments are part of the syllabus. So this is pretty much it for the new limit theorem. You can find this applet as well as this article at my website. I shall put the links in the comment section when I upload the video to YouTube. This is the New Calculus channel. I'm John Gabriel. Thanks for joining me. Till next time. Bye.